All right, this will be the last official video for the class. I'll do a review video as well to kind of go over what you need to know for the last test, and then another one for the final. But as far as material to learn, this is the last one. And this one is called chi-square. There's some math. If you don't like math, sorry, there's a little bit of math in biology. And this has to do with something called hypothesis testing. In other words, I have a hypothesis, a theory that I think is correct, and I've gathered numbers about my hypothesis. How do I make sure that the numbers are, say, far enough apart for me to be able to say that yes, something is going on here, versus no, nothing really happened. They're really not far enough. It was just random. So in other words, you do something and you're asking, maybe you're playing ping pong with somebody, and you play 20 games, and each of you win 10 games. Well, and you want to claim you're better than the other person. Well, that isn't going to help you any, because both of you won 10 games. And maybe one person, we did 20 games, and you win 9, and the other person wins 11. Is that one different, better enough to say that statistically you're better? Maybe not, because it's only one game. If you played 100, it might come out where, the other way, where the other person, where you win more games than them. And the idea here is there a way to test that, given just a certain number of trials, is what we'll call them, they're experiments, how many times do we have to repeat the experiment to really be able to say, yes, this, like if you're playing the ping pong, yes, I'm a better player than the other person. Or in the case of an experiment, yes, when I add, this chemical to the bacteria, they do something. Let's say, I don't want to say die, but let's say they change, they turn certain genes on and off. Maybe you add a chemical, and these bacteria, some of them, when you add that chemical, they turn on a gene. And maybe there's only a certain number of them, but we repeat it over and over again. And yes, if they do it often enough, hey, you can say that yes, this experiment shows that that did happen. And the example, though, that I'm really going to use are with some cows, because this is an easy example. So let's say you own 1,000 cows here. Okay, let me do it over here. I have 1,000 cows. All right, and I have them in Texas. This is related to evolution. And in Texas, let's say 200 of those cows are white. Their fur is white. All right, and 800 of them they're kind of brown. The technical name for it is roan. They're kind of a reddish brown color. And okay, no big deal. 200 white cows, 800 roan cows. All right, what are we testing? Well, what we're going to test here is to see if adaptation has occurred when we move our 1,000 cows. We're going to move them, all right, to a different state. We're going to go to Wyoming. And we let those 1,000 cows breed a few generations. It might take a few years. And then we retest this, and we see that we now have 400 cows. All right, that are white. And we have 600 cows that are roan. Wow, that's a big difference. You've doubled the amount of white cows in, 3 or 4 generations. You still have 1,000 cows, but you've doubled the number of white cows. I would say that's enough to say that, hey, these cows have changed when we went to Texas. What happened? Well, they may have adapted. Realize these cows, when you're in Texas, there's not a lot of snow, but there is snow in Wyoming. So what might be the difference? Well, maybe there are wolves or coyotes. And in Texas, being white just makes you stand out and get eaten. All right, so it's not an advantage to be a white cow in Texas. But when you move to Wyoming, especially in the winter, there's snow. And now you're camouflaged, and maybe the coyote or the wolf doesn't notice you, and so therefore you have an advantage over the roan cows. And so you can reproduce, and therefore you live longer, you reproduce, have more cattle, more calves. Basically, white cows have the advantage, so you see the population of white cows go up and the population of roan cows go down. Well, this is an example of how we would test to see if natural selection is occurring. In other words, in fact, this would be natural selection. In other words, we can test, all right, if this is a big enough number to have go from 200 to 400, we can test to see if the what would you say? If the number of cows increased, is the number big enough to say it's not random? In other words, I'm going to tell you that doubling is definitely bigger than it should be. Okay, so a random. This is not going to be random. But how would we do this? How would we tell whether or not the number of cows increasing from 200 to 400, if that really is enough to prove that that natural selection occurred and it wasn't just a random thing? Well, you do that using this equation. It's called the chi-squared. All right, chi-squared equation. And what it will give us a number. It'll give us this thing. This is the chi symbol, and it's squared. So this answer to what we do here, all right, is going to tell us whether or not this was a random event, or if, like, it could occur just randomly, or if indeed something did occur. And in this case, it would be that natural selection occurred. In other words, there was a change in the number of alleles present in your population. So here you have 1,000 cows, and there are so many little a's. Let's say white is little a, and roan is big A, little a, and big A, Or homozygous dominant and heterozygous. This one is so if this number changed, the allele numbers change. So I'm going to just make up some numbers here. If we had had a little bit more time, we would have learned something called the Hardy-Weinberg, but we're going to at least learn chi-squared. This is the easier of the two. So we're just going to say that there are a certain number of alleles in the population. And I'm going to tell you that, let's say there will be twice the number of alleles since there are 100 cows. So we're just going to say that there's a number. 600 out of 2,000. There are going to be 2,000 alleles because there are 1,000 cows and each one of them have a big A or a little a. Either two big A's, two little A's, or a big A and a little a. So 600 out of 2,000. And we'll say that this is the number we have in Texas. And then when we go to Wyoming, let's say the number of little a's has increased to 800 out of that 2,000 alleles. So that wouldn't be the right answers for over here, but we'll just use these, and this is our Wyoming number. I'm not being exact here. I'm just showing you an example of how to use this equation. So we need to find this number, 600 divided by 2,000. So here I'll start my calculator here. So 600 divided by 2,000 would give us a number, 0.3. All right, and the other one is 800 divided by 2,000. And that's 0.4. Okay, easy enough. Not hard numbers to work with. So on the test, I'll give you two numbers. And what you need to do is you need to know where to plug them in and find this answer. This is an easy equation, especially the way I have it set up. And all you have to do is take one of these numbers, and it's going to be O, and the other is E. E is the expected. Expected means you move from Texas to Wyoming and you get the same thing. So in other words, 0.3, and then you move to Wyoming and you expect to get 0.3. So our expected is always going to be the original number. Even though O is observed, this stands for observed, but you can think of it this way. The one that we start with, the first place we live in, if you think of it as being at moving cows, is going to be 0.3. And then the other number, the 0.4, when we move and it changes, all right, this is our starting point, this is what we did after. So this is, think of it as a time. This is time 1, and this is time 2. All right, well, the time 2 will always be your observed. So that one's 0.4. So we just do this. And so what is 0.4 minus 0.3? Well, that's going to be 0.1. All right, 0.4 minus 0.3 gives you 0.1. And then we have to square that. So, okay, 0.1 times 0.1 is 0.01. Really easy numbers here. So on the top here, I'm going to end up with 0.01. Now on the bottom, we just use our expected. Now what is the expected? It's the one we started with. So it's going to be 0.3. Actually, it's right here, right under here. So 0.01 divided by 0.3. All right, so 0.01 divided by 0.3. And our answer is 0.033. All right, 0.033. Did I do that right? 0.01 divided by 0.03, and it's 0.33. Yes. So our answer, it's 0.33. Okay. So our answer to the chi-square is 0.3. Let me do that again. I was sick earlier in the week, and I am not 100% here. 0.033. Yeah, I had it right the first time. Okay. Let's see. I have an eraser here somewhere, don't I? Yeah. All right. So let's do it this way. So 0.033. It's a very tiny number. Now, the magic number, all right, if you get, and we don't have time to go into the math behind it, which you're probably really happy about that, why I'm choosing this number. But this is a number, and I will give you this number. But it's 8481. Oh, I should have looked it up. 84. Oh, it's 3.481. It's either 3.481 or 841. Let me look it up real quick. Let's see. $3.841. Okay, so it is the other way. All right, real quick. So 3.841. So think of it this way. If you go over this, then it's significant. And here, this moving from 0.3 to 0.4, that was not significant because it's only 0.033. And so if you get something like 0.033, then you're close to 0. 0 is what you get if this didn't change at all. In other words, if this had been 0.3, then your answer would have been 0. And if it's 0, all right, then there was no change, and obviously there has been no adaptation, no natural selection, because your numbers didn't change. All right, but if they did change, even a little bit, you need to check to see if it's significant. And a change from 0.3 to 0.4 is obviously not significant. All right, you only got 0.033, which is way below 3.841, a lot closer to 0. So if you get below this, then there is no change, nothing you can prove. All right, that's triangle is a symbol for change. All right, now if you get over 3.841, then there is, and you can say that something happened. All right, you can say that these numbers are far enough apart that we think whatever we did, our experimental variable that we changed, significantly changed the results. And we now can say that our experiment was a success. All right. If, however, you're below this number, you cannot claim that your experiment was a success. And we don't have to go into the idea of where I got the 341, but I wish we did. But you can take a statistics course and they will tell you, I am sure you'll spend a long time learning about why this number was used. But what we need to learn is just how to use this. If you have a hypothesis, your hypothesis is we moved from Texas to Wyoming and the number of cows increased. Did it increase in a large enough amount for it not to just be random fluctuation? If it did, well, we're going to have to, you can't just say that it did. All right, it looks like it did, but did it really? All right, and when we calculated ours and we had 0.3 and 0.4 as our answer, so 600 out of 2,000, and this should be 2,000 here, and we went up to 800 out of 2,000, that just wasn't enough. All right, so our number 0.3 and going from 0.3 to 0.4 just wasn't enough for us to claim that this was statistically significant. If we had gotten a result that was over 3.841, we would have been able to say, yes, there was a change, that it was not random, and we now can claim that our experiment was a success, or we can claim that, yes, natural selection occurred when we moved our cows from Texas to Wyoming. Okay, so this is our last video besides those that are going to review and kind of tell you what's on the exams. So the final, I'll do a review for the final, and we'll also have a review for this final test.